Okay, so this talk is based on these two preprints. One is done Wen-Chen, and Fuji-kun is my research associate. And also like the other preprint is like Yaozong Fu, so he's my graduate student. Okay. So so today I'm going to talk about some properties of topological phases. But when we say topological phases, it basically means two completely different things. Like one is known as like primitive protected topological phases, sometimes called trivial phases. And the other one is like topological ordered phases. And these are kind of confusing but completely different kind of phases. So what is their properties? The first class is symmetry protected topological phases. So this phase usually have these properties, like it has unique ground state with excitation gap, and it is only stable against symmetry preserving perturbations. So if we allow to break the symmetry of the model, basically it's just a trivial. And many of these classes of phases can be connected to product states by local unitary transformation. By the way, should I remove my mask? I don't know, like
entirely up to you.
Yeah, okay, like this is like really common in Japan, but I feel like I found who are wearing masks. It's completely opposite. Oh, I didn't realize. Okay, and all right, and also like the expectations of these phases are trivial. So let me so these features makes a completely sorry, like I came to Japan from Japan yesterday, and I had a jet lag, and I woke up 11:45 before midnight. Which is crazy, but okay. So I'm just saying like these are completely different. So for the order phases, we have ground state degeneracy, and it is stable against any perturbation. So we don't have to respect the symmetry of the model, although the model has some symmetry. We can break it, but still, these topological order phases remain topological, and it cannot be connected to product state by local unitaries. And we have excitation which is kind of fractionalized. Okay, so starting from electron system, you can have excitation with fractional charges or separation of spin and charge degree of freedom. Okay, so these are the features of topological order phases. Okay.
And by symmetries, you mean unitary symmetries?
That's right. That's right.
Unitary symmetries.
It can be unitary symmetries, but I'm not talking about like a generalized symmetry here. I'm just meaning like a very just simplest internal global symmetries or unitary symmetries and unitary symmetries. I don't want to hear it going into like higher form symmetries or the and okay, so I'm going to kind of ask this standard understanding by some interesting example I'm going to share from now. So the simplest example of topological ordered phases is Z2 triple chord model. So I think this is everybody in this room is familiar with this model, but I'm not familiar with this model. Okay, great. So I want to discuss this model in detail so that the model I'm going to introduce today is a generalization of this model. So it's very, very important that everybody knows this model very, very well. Okay. 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 So this model is very, very simple. It is given by sum of two terms. Okay. Each term has some sub-index V and P. It means this model is defined on square lattice, and spins are sticking on each link. Okay. And by brackets. Bracket means like this square, right? And this bracket term contains these four spins. And the vertex term contains these four spins. Okay. So for each vertex, I have a product of X operators that are A term. For each bracket, I have product of these four spins, B component spins. That is my B term. And the most important properties of these products is that they commute with each other. So X and Z spin do not commute, but when we try to compute their commutation relation, we notice that each of these terms contain two common spins. So x and z anti-commute, but this x and z anti-commute. So after all, I think they just commute. So these are terms in the Hamiltonian, and they all commute. So the ground state given by like a simultaneous eigenstate is plus y eigenvalue of these operators. Okay. And we assume periodic boundary condition. So it means that my spin model is defined on torus. And oh yeah. And as I said, a squared and b squared is 1. So the eigenvalue of a and b term can be like either +1 or -1. And any state with eigenvalue +1 for all vertices or brackets is a ground state. Okay, so this, and I forgot to say, like, this is like a spin model, and I have a two-level spin. So this is like a Pauli operators x and b. Okay. Any questions? Good.
What is degeneracy of the kind of state?
The ground state of this model. Yeah, I'm going to explain for now. Yeah. Yeah, and so we have global constraints. So if we multiply all vertex term and bracket term, we just got 1. So that you can see from here. So in this case, you make a product of all bracket terms. Then you have this v spin in common with this bracket and this bracket. So it appears twice. So we have identity, and that is true for every spin. So you have this identity. So this means that not all stabilizers, not all of these terms are independent of each other. So we have some global constraints. And this is related, like we have Wilson loop operators. So Wilson loop operators are product of spins like this. And if we multiply them together, we realize that these Wilson loops commute with Hamiltonian. So you can assign eigenvalues of these operators. And we start from the Hamiltonian ground state phi. Suppose that it has eigenvalue +1 for this Wilson loop operator. Then using this commutation relation, you realize that you can restart your full degenerate ground state. You can construct it this way. So in this model, you have 4 ground states. You don't have any symmetry breaking, but we have stable degeneracy. So let me summarize what we have seen in this model. We have ground state degeneracy. More generally, like if you change your manifold, so far we were discussing this model on torus, but you can change this manifold, and then you will see this kind of behavior. You can compute topological entanglement entropy of this model. I will give the detail of this definition of entropy, but you see that it is given by this number. And you also know that if you look at excitations, there are basically 2 times 2 anyons, like just electric particle and magnetic particle, and they have some mutual statistics. Okay, so this is the key features of this triple model. And I want to introduce my model. I want to explain the feature of my model. So I introduced some parameter A to the model, and I changed the model from 2-level spin to n-level spin. Then I realized that it has these features. So first, the ground state degeneracy depends on the system size. So this length is L1 and L2. And so when both L1 and L2 are multiple of n-1, then ground state degeneracy is n squared. However, when L1 and L2 is not a multiple of n-1, then ground state is unique. So this is the kind of most surprising feature of this model. So for example, when your n is, for example, 11 and equal 2, then according to this rule, it says that ground state degeneracy occurs only when L1 and L2 are multiple of 10. So that means For example, if L1 and L2 are both multiple of 10, you will see ground state degeneracy, but otherwise you don't see the degeneracy. And but this is kind of crazy, like the quantum dimension is 11 and they have 10 by 10 spins. So it means like, this huge quantum dimension, so it cannot be reached by any numerical method, right? Yeah.
So people do much more than that in lattice Monte Carlo.
Oh,
I mean, 10 by 10, I don't mean that they work with 11 to the 200 states. I just mean that lattices of 10 times 10 times 10 times 10 are,
oh, is that right?
not out of reach, right?
But does he have a same problem if n is not 2?
Well, I don't know about.
Yeah,
but I
maybe.
mean, lattice Monte Carlo could. I mean, that's
Yeah, but
the
okay,
reason
okay. Yeah, okay, maybe they some method, but okay, I don't know if that's possible.
I don't know for.
Yeah, okay, yeah.
But like people do QCD, right? The number of states
I
per
see.
lattice site in QCD is
Oh,
much bigger.
well, I didn't know. Okay,
Yeah.
okay, but
We don't have exact solution.
yeah, but okay, but I was just saying, I'm just saying, okay, give them some model.
Yeah.
You don't know the details of the model, so maybe I will start from, if I cannot solve it by hand, right? I will maybe just put it in Mathematica and try to try to perform exact diagonalization.
Yeah.
And I'm saying, okay, I keep seeing, I change my system size from 1 by 1 to 2 by 2, 3 by 3, 4 by 4. I keep seeing, ground state is unique with the excitation gap. Then I will kind of start to believe that this model is kind of trivial. But only after I reach 10 by 10, I suddenly, start to see some degeneracy, right? So I didn't know like this kind of behavior occurs. And that's all I'm saying. But independent of system size, I always see some topological entropy. So this is a feature of my model. So and also like we will have anyons. So if you look at the excitations, this model is really topological in topological order phase.
So can I ask you a question?
Yeah.
I would think if the power is 100, but you have 200.
Oh yeah. So this is because like I have 2 spins per each square. Which the spins are sitting on a link, not on the vertex.
Okay.
Yeah. Thanks for the question. Yeah.
What happens in the continuum limit when you take L1 and L2 to infinity? Basically, then you would have not like 10, but let's say.
Yeah. So like I'm talking about
generally-
I'm talking about system size dependence, right? So this L1 and L2, this kind of finite size. This is So this is basically just a finite size defect, right? And I don't know how to take smooth continuously or yeah.
There's one way to say that this system has UVIR base. You cannot, some properties that you cannot separate the UV from the IR. So that's why the system side is shown.
Maybe I think I will explain the detail of this model first, and then we can discuss it later. Yeah. Yeah, and also like so here I was explaining my results for some particular choice of A. So I have parameter A, and for some A, like this is the feature of the model, and I have some analytic result for more general case. But maybe I should skip this first. Yeah. So let me update, using with the result I obtained this model. Let me update this general understanding. Okay. So I said, like in SPT phases, ground phase is always unique with the excitation gap, and for the order phase, we have ground phase degeneracy, right? But I think like, we need to update this understanding. So symmetry-broken topological phases, SPT phase, the ground phase is unique for any choice of L1 L2. So you can change your system size. You always see that ground phase is unique. So that's the property of this SPT phase. For topological order phase, we have seen that the ground phase can be unique for some choice of system size. So but for some choice of system size, for some sequence, right, you will see that ground phase degeneracy. So you have to be careful about this kind of system size dependence. And all right, and also like usually anyone must appear in pairs, but in my model it's kind of crazy. A single anyone will appear, but it is still an extended object. So you cannot excite the anyone locally. Okay. Yeah. Okay. So let me give you the detail of this model. I just kind of skipped everything. But I just wanted to say like this model has some interesting feature. So maybe we will see the detail of the model. Okay. Yeah. So from now I will give the definition of this model in detail and look at the simplest case, and then moving on to the interesting cases. So in my model, I have spins on each link, but each spins are n-level spins. So it's not two-level spins. It's a generalization of two-level spins into n-level spins. And so Z power Z operator is generalized to this 1 omega squared, and omega is defined this way. And X operator it changes level of Z by 1 unit, right? So it's like this kind of operator. And both of X and Z are not Hermitian anymore. So you have to distinguish X and X dagger carefully, okay? And we have coordination relation Zx equal omega times Xv. So this is a generalization of Zx equal minus Xv for n equal 2 case, okay? And we have this kind of d to the power of n is always 1. And yeah, everything else is really the same as usual spin. In particular, a total Hilbert space dimension is n to the power of 2 times L1 times L2. Any questions? Good. Yeah. So I write down a toric code model using this n-level spins, but the point here is that I have parameter A. So usually like I have so usual n-level toric code model is written in terms of just n-level spins, but parameter A is 1. So you set A to be 1. That's the usual toric code for a Zn toric code. But I generalize it with integer parameter A. Okay. But you see that still these terms commute with each other. So I have Z, I have X to the power of minus A here. So they give you the phase of omega to the minus A. But I have Z A to the power of A here and X. So you have opposite phase from this here. So they still commute. Okay, so this is still commuting Hamiltonian. So I have Hamiltonian like this, and I impose periodic boundary condition. And this model is perfectly translation invariant. So I'm not talking about like a defect even, at least in this representation, the model is really translation invariant. Okay. And this parameter A is very, very important. And so far in the literature, before our work, A equal 1 example has been discussed frequently. However, some of these authors write down this model with parameter A equal n-1 without realizing that the property of the model is very, very different from A equal 1 case. Okay.
Does it have a rotational invariance?
I don't think so. You mean like a four-fold rotation symmetry?
Yeah.
I don't think so. Yes.
And can
Why
you,
don't you put A's on the rest of the bracket? -1, D -1, D minus A, DA, right? By 3.
Yeah, so this is very important. Like if you change one of them, these two terms do not commute with each other anymore.
Oh, I see.
Yeah, so I design it very, very carefully so that I can keep the commuting Hamiltonian part unbroken, but still I generalize with some parameter A.
Good.
Yeah.
so if you replace this X by X to the power of B.
Yeah.
I can do it. Yeah. So like
Z.
yeah, so X direction and Y direction can be chosen independently. So I can do this, for example, like in X direction, I put power A1, and Y direction, I put power A2. That's possible.
And you have to do the same with Z.
Yeah,
The same number thing.
Yeah. But for now, for simplicity, I'm setting like A1 and A2 to the same. Yeah.
Actually, so is there any like symmetry reason why I have to choose one specific A? Why can't I just sum over term with different little a in it, right?
Different. Oh yeah, I mean you can do it. Yeah,
Yeah,
but,
but okay, so now suppose have both a equals to 1 and a equals 2 in the same model. So
but yeah, I think if you do so, like you will lose in commuting nature of each term,
I'm gonna lose that. So
like yeah, this term commute with this term only when
okay.
this two A matches, right?
Yeah, I just wonder that whether all the new features, right, is stable against adding terms as I described. I mean, so if the terms I described have no like a symmetry restriction to to make sure they are 0, right? So one forbid them to be there. And if they
Okay, so like at least for this study, like like I wanted to solve this model by hand. So like I kept in our attention to the exactly solved model, and this is the best we could go. But maybe it is possible to generate this like this. But so
sure.
so
it's gonna be better if there's some reason that those terms are 0, right? Yeah.
But I think like for this talk, I think it is sufficient for me to just focus on this simplest model.
Sure.
And even with this simplest setting, I already get some interesting feature. I think that's kind of important, because from the textbook I already learned, topological order phase, ground state degeneracy, the real phase.
All topological phase are stable against symmetry allowed for the basis.
Right.
That's an important feature of the topological order to be defined in the first place. No, so for the polygon model, right? So I can turn on terms which actually do not commute with their vertex term.
Yeah.
Still,
that's right. So
it's still
that's
stable, right?
Yeah.
So I wonder whether it's still the same case here or not.
Yeah. So I believe that this model still has such kind of stability against symmetry, not preserving terms. That's fine. But I want to first establish the ground degeneracy for this model first, and then you can discuss the stability, right? Yeah. Okay, but I hope that at least the definition is kind of clear, at least for this model. Okay. Yeah. So let me construct a ground state. So ground state can be constructed this way. The eigenvalue of this bracket operator and the vertex operator are just 1 omega to the power of n-1. And in state with ground state plus 1 for all vertices and brackets is a ground state. So I want to construct this kind of state. And that is easy. I can start from, for example, a ferromagnetic state. So I have a state for I0. So it has eigenvalue plus 1 for all Z operator. Then starting from this state, I can apply this projector. Then you realize that this state, P acting on this phi naught, is a ground state which has eigenvalue plus 1 for all vertices and brackets, and you can show that kind of property from this kind of algebra. And okay, as I said, A1 case is a standard tripod model. And I can form a X loop operator and D loop operator, and their coordination relation is given by this. I have, instead of -1, I have now phase omega. So this is really the generalization of standard Z equal n equal 2 tripod model to the n level spin. So ground state degeneracy is n squared, and you have topological entanglement entropy, and you have n squared species of anyons. And so far I didn't explain the calculation of entanglement entropy. So here, let me explain how we compute it. So we follow this prescription by Kitai and Fresco. So I take like 3 neighboring regions like ABC, like this, and I compute entropy of each region SA and SB and SC. And SAB, BC, CA, and SAB, and I combine them together like this way. Like this is just to avoid some artificial contribution from the choice of the boundaries. And yeah, but like I thought this is the safest way of computing the entanglement entropy. And the entanglement entropy for each region is defined this way. Like I have a density matrix for that region. And I just compute rho, log, rho, and trace over the in the system. And but I didn't use this definition of the entropy. I use this useful formula that can be obtained for this kind of projective Hamiltonian. And basically, what we need to do at the end is just to compute the number of spins in the region. So NR is the number of spins in that region. So this is, say, 1, 2, 3, 4. So NR is 4. And MR is the number of generator of G. So this is G is the term in the Hamiltonian. So basically, like you count the number of terms in the Hamiltonian in this region. So I have for this region A, right? So I have one bracket. So MR is 1. That way, like the calculation of entanglement entropy is very, very simple for this class of Hamiltonian. And from that I obtain this minus log n result. Okay. And also, like I said, in Brown-Setter degeneracy can be computed very easily from this using like this Wilson loop operators. But you may wonder, there can be additional degeneracy, central degeneracy in this model. But I can prove that there is no such kind of thing by constructing all states by hand, right? Like you can construct, you can construct all like n to the power of 2 L1, L2 states by using open strings. So there is no accidental degeneracy. The number of degeneracy is really given by this standard case. Okay. Right. So also like there's another simple choice, A equal n. Then if you set A equal n in this model, z to the power of n is just 1. So this model is really like this kind of two-spin model. And this is not easy, not interesting at all. Like this is completely decoupled. And basically the Hamiltonian ground state is really like a product state. So ground state is unique, and entanglement entropy is just 0, and no anyons. Okay. So these are two kind of trivial cases. And I want to move on to more interesting cases. So far, what was important was loop operators. But when A equal 1, I can just use Wilson loop operator. And but that is no longer the case. If you have parameter A here, then this operator does not commute with this bracket operator. So instead, what I have to do is to make a product of X operator, but not just the uniform power. I need to change the power. If this operator is power with power 1, the power of this operator is A squared. That way, like I need to change the power of this operator. Then this part, x times x to the power of A, commute with this bracket term. And there's another bracket term here, right? I need to commute with this x to the power of A and x to the power of A squared, right? So this loop operator commute with every term in the Hamiltonian. But then there's a constraint, like I have x to the power of L1 minus 1, but this must be connected to this operator, right? It's power 1. So here, the system type becomes important. Okay. So this term commute with boundary bracket only when a to the power of L minus 1 equal to 0 modulo n. Okay. And okay, so I also have excited states which shows interesting features. So if you apply x operator to the ground state, I can create a pair of anyons, like omega and omega to the power minus a. So that is because yeah, you can see it, right? Like if you apply x operator, yeah, x operator here, their combination gives you omega. But if you have x operator this side, then the power is a to the minus a. omega to the minus a power, right? So the charge of the excitation is not the same in this. And if you want to move these anyons, right, you have to use not x operator, but x to the power a operator, right? Then every time you move anyons, the charge kind of change, like from a to a squared and a cubed. So moving anyons must change your must interchange anyon species. Okay, so this is the reason for the non-trivial grounded degeneracy pattern. And yeah,
One question about, so the previous slide, so, so what's the statement then? You say when you translate an anion, what is the permutation?
yeah, translation just means, yeah.
What's the permutation? I guess I'm saying you said it permutes, but what's the actual permutation?
Yeah, so I have anyons with charge 1, 2, 3, n. Yeah, n is actually just trivial particle. So this, I want to use this, 1, 2, 3. These numbers are the charge of electric charge or magnetic charge. I'm just saying, every time I move the anion by applying this X operator, the charge cannot be conserved in the translation. If I move this particle by one step, because of this reason, this operator doesn't commute with Hamiltonian. I need to do x next to x will be x to the power a to the power a squared. I need to the string operator. The power cannot be chosen uniformly. So this means if I want to move this anion by 1 unit, I need to multiply not the x operator but the x to the power a operator, and the charge. Yeah, so here this figure shows this anion is moving by 1 unit, right? This one by 1 unit, and the charge is changed from a squared, a cube.
So you're saying translation changes you from charge 1 to charge a?
Yeah, right.
Just maybe I'm getting something in mind. But doesn't translation if a is not relatively prime to n, then
right. When a and n are not prime, then this means something crazy happens. It can the particle becomes kind of trivial at some point.
doesn't translation have to preserve the order of the anion? Symmetry.
Yeah, but at least you can see. So that means there's some restriction on the possible charges of anyons. So there is no n squared anyons when n and a are not prime, not coprime.
Oh, I see. I'm
Yeah.
sorry. So there aren't the labelings.
The labeling must be carefully set up. Yeah. Good. Yeah. So okay. This is a kind of same thing, but now you know why there can be a single anion in this model. So I have a loop operator, but this is a kind of fake loop operator. I have this loop operator, but suppose that I said about the system size must be a good one, so that there's no mismatch at the boundary. But suppose the system size is kind of wrong, then if there's a mismatch at the boundary, then that kind of loop operator will create anyons at the boundary, right? So here I'm just saying, if I use that kind of fake loop operator, I will create a single anion at the boundary.
Just a quick question. So
Yeah.
the Hamiltonian is not frustrated, right? System sizes.
Hamiltonian is frustrated?
Not frustrated.
Not frustrated, right. So it's really commuting Hamiltonian for every system size.
So commuting and also the ground state is in lowest energy, I think. State.
Right.
So
Yeah, great.
this single thing can then move around on the lattice for free or no?
I think you can move it. Yeah. So this can appear any place, but I'm just saying, I try to make a loop, but depending on the system size, I have a mismatch at the kind of theme of this room, right? And steam can be put anywhere.
Sure.
Yeah, so, but that kind of single anion will hop around, but it cannot be created locally, right? I have a loop operator which has some seam, which has some kind of mismatch. So
For the cases when the ground state's unique,
mhm.
do you know if that ground state can be disentangled into a product state with a finite depth circuit?
So as I said, like if I compute entropy, topological entropy is non-zero. I thought that's a kind of proof that it cannot be. Yeah. Yeah, great. How many time do I have?
10 minutes.
10 minutes. Okay, yeah. So let me wrap up. Yeah, so I also wanted to talk about global constraints. So when we form global constraints, I said we need to make products of all bracket operators, like vertex operators. But again, I cannot make a product of vertex operator at every vertex. Like I need to change powers like this way. Like if I have a operator here, I have a to the power a operator, and that way, like I need to keep changing the powers of these operators like this way, so that it commutes with Hamiltonian. But that again, like this kind of global constraint requires the matching of the system size at the boundary. And okay, so I don't have time to explain the derivation of this result. The ground state degeneracy is given by okay, I skipped this part in the introduction. But anyway, like okay, in general, so given system size L1 and L2, and given the integer n and a, I have a formula. The ground state degeneracy is given by this formula, and I have this species of anyons, and the Na is defined this way. Yeah, so the Na is the largest divisor of n that is compliant to A. So this related to your question, the number of anyons must be chosen this way, like n. So the number of anion is given by the kind of coprime part of n.
Is that squared? The number of anions is Na squared? Or...
So like electric particle and magnetic particle. So I have Na squared. Yeah. Na species of anions. Yeah. Na squared species of anions. Yeah. Great. And so let me give you one more detail. Like suppose that n can be prime factorized this way. Then there's a mathematical notation, like radical of n, which is a product of all prime factors of n. But this power is just one. Okay. So we have a rule. If parameter a is a multiple of radical of n, then Na equals 1. This means that there's no anyons and there's no ground state degeneracy for any system size. So this is the SPT phase. And we see that sometimes this model gives you non-trivial SPT phase, and sometimes it is really trivial, like product states when A equals n. Okay. But when A is not a multiple of radical of n, then this is topological order phase, and you will have some kind of degeneracy for some specific system size, some sequence of system size. Okay, so this is all what I wanted to say about this model, and I want to briefly comment on the INT model. You can play the same game for this INT model, right? So I have standard, INT model is a kind of canonical model that is like that shows ground state spontaneous symmetry breaking. So you have symmetric phase and you have symmetry-broken phases, and these can be distinguished by order parameters. And to see this kind of order parameter in quantum model, you have to be careful about the order limits. Like you introduce symmetry breaking field first, and then compute the value of order parameter. You first set symmetry breaking field to 0, and then take large system size limit. Then it is always 0. But the other limit, you will see kind of spontaneous magnetization. Okay. So what I'm proposing here is to do the same thing for this eigenvalue model. So I have generalized eigenvalue model for any level spins, and I have parameter A. And what happens? We found that yeah. So we found that sometimes ground state is unique. So please look at this here, this inset. So other function parameter G, and this is a difference from the ground state in finite size and first excited state. It has a gap, and the gap close at G equal 1. So it means there's a kind of this is a critical point, but in both sides you have unique ground state. So this is kind of different from usual eigenvalue model. But still, you see the non-commuting feature of this limit. Like you first apply symmetry breaking field and take relative system size limit. In the when G is small, you see exactly the same behavior as in the symmetry breaking phase of eigenvalue models. But when G is large, it just product state, so there's no symmetry breaking.
Sorry, so,
Yeah.
since the gap close at precisely G equals 1, is there like a same duality between like G plus?
Yeah, there's a duality, yeah, like the usual eigenvalue model. So usual eigen case is like when G is smaller than 1, you have ground state degenerate, so like excitation gap is 0. The difference between first excited state and the ground state is kind of 0 in the usual eigenvalue model. But what I'm saying here is that if we introduce parameter A to the model, depending on the system size, you can realize this situation. Like ground state is unique, although the system is in the symmetry-broken phase.
Sure. So this is primary duality for any n or
No. So Kramer's degeneracy is usually discussed in the usual eigenvalue model.
Yeah.
Yeah, and that is the duality between like G and 1 over G, right?
Yes. Here. Sorry. Yeah. So for other n and a, right? For n equals to.
Yeah. So okay. So this is the usual. Yeah. Sorry. I don't have enough time to discuss this model in detail. But okay. So this is the usual n-state clock model. That is the generation of transverse field eigenvalue model. And in this case, I have a duality between 1 and 1 over G. Yeah. And we have when G is smaller than 1, we have symmetry breaking. When G is greater than 1, symmetry is not broken. And at least for n equal 2, 3, 4, right? When n is greater than 5, you have 2 critical points, and so like that further detail. So, but so let's say like n equal 2, 3, 4. Okay, for now. Then G equal 1 is a critical point. So that feature remains true even when we kind of introduce this parameter A. But what I'm saying is that ground state is kind of unique in both sides.
Okay.
Yeah.
So for the symmetry broken state, is the ground state something like a cat state, or
No, actually it's really just a product state.
so it's products on
yeah.
both sides?
Yeah.
I see.
But yeah, this is really kind of crazy. Like we don't have exact symmetry, and we don't have ground state degeneracy. But still, if you introduce parameter epsilon like this way, like usual like external field, like this is the order parameter. So order parameter times parameter epsilon, right? I still see the non-commuting nature of this, epsilon and system size B. So that's what I mean by symmetry breaking. And
So do you know what kind of CFT that is actually equals 1?
yeah, okay, that I don't know. Yeah, but maybe I'm running out of my time. So basically this is the summary of my talk. We introduced an interesting model which contains parameter A, and we have formula for ground state degeneracy. So and in particular, we are saying maybe this kind of clarify sharpen our understanding of topological phases, like symmetry-broken phases and topological order phases. In particular, in this case, you have to be careful about the system size, and we can do the same thing for eigenmodel as well. Thanks so much for your attention.
We have like 10 minutes to discuss. If there are questions, yeah.
Okay, so back to that topologically. For the cases when the ground state is unique, you said that the topological entanglement is still greater than 1. But the ground state supports no anyons. So does that?
We have anyons, right?
Okay, so the ground state is unique, but it does support anyons.
Yeah. So yes. So
I was going to say there were no anyons that would be a counterexample to this formula for topological entanglement and in terms of the total kind of dimension of the anyons, but there are anyons.
Yeah. So wait. First, calculation of topological entropy. Here, what I want to say is that the calculation is very local. It doesn't care about the boundary, right? The system size is kind of irrelevant for this calculation. So independent of the system size, the result is always the same. So, for example, like you can expect the kind of maximum number. So NA here.
I see. So the result for that is independent of system size.
That's right.
But the anyon spectrum changes.
Anyon spectrum. So
the total number of anyons.
Yeah. So number of anyons doesn't depend on system size. So that is given by
that was like NA squared.
Yeah. Anyway. Yeah.
Oh,
Anyway.
I see.
And NA. Yeah.
That just depends on NA.
Yeah. So the definition of NA was like the largest divisor of N that is coprime to A.
Okay.
Yeah. So this doesn't depend on depend on system size. Yeah.
When you compute the topological entropy, is it possible that there is a dependence on the size of the partitions? So heavy.
Yeah. So we wanted to kind of remove such kind of dependence as much as possible. That's why we do these 3 system size things. But still, we realize there's kind of additional contributions, and I didn't have time to talk about that. But there can be such kind of dependence. And so that is in this case, so for example, when suppose that n equals 4 and a equals 2, then n and a are not coprime with each other. In particular, a is a multiple of radical of n. So radical of n is 2 in this case. So a equals 2. So this is like an SPT example. This is SPT. So normally you expect that the entropy is just 0. But in this example, we found that it's kind of non-zero. But this is accounted by a so-called spurious contribution, and we realize that this phase corresponds to the subsystem symmetry-broken topological phases. So that kind of things happens in this model. Thank you for the question. Yeah.
So for your stabilizer code, can I understand them as some type of gauge theory that the local charges, the end charge is not conserved, but there is a spectral Zn charge that if it cannot grow, but it grows exponentially, this is the
Special. Yeah. So I think that's a very interesting question, and I think you're.
Yeah, for A, if it's Radolf n or multiple of Radolf n, it's special in the case that this symmetry only acts on a finite degree of freedom, even in thermodynamic limit, because as long as we are larger than the Radolf n, then it turns out that all of these sites carries 0 charge more. It's somehow like a local symmetry, and once you gauge it, you still won't get any order.
Yeah. Okay. That I think I need to discuss with you in more detail. I cannot immediately answer to that question. Yeah, can we discuss it? Yeah.
So in this model, does anything go wrong immediately if you make a non-integer?
Non-integer. Yeah. How do you
still commute?
Yeah. How do you define it?
I mean, x square root of x is 1.
Oh yeah. Okay. Yeah, if you can make it well defined, then I don't see any problem. As long as
This is always.
And well, degeneracy in the formula may not be even an integer. I don't know what not integer means. So
Next to any. Right.
Yeah, but yeah,
You have to choose a branch.
yeah, you have to choose the branch path, right? Yeah. Yeah,
actually, so you say like well, I mean, for the DN protocol is like mutual assignment kind of field theory description, right? So here actually, do you have anything like that?
so continue description.
Yeah, some flavor. I mean.
Oh yeah. So like okay, so
Some kind of
So that-
assignments.
yeah, so okay, so if you look at our paper, you will see that you will notice that today I skipped one section completely. That section is written by Menchen, and he developed field theory for this model. Yeah, his explanation was that this could be understood as the kind of in terms of defect lines. So today I explained that I have a in my model, anion cannot be moved without changing its charge, right? But that kind of the interchange of anions can be understood in terms of symmetry defect. So like I have like defect line, and when the anion passes this defect line, it changes anion species. And I can understand this model in terms of this kind of the symmetric arrangement, defect line that theoretically arranged in the entire system. So I can do the field theory for the standard, so I can understand this model as a usual toric code, but I have defect lines everywhere. And so
Can I follow up on this? What is the nature of these defect lines? Are they topological operators? Are they invertible? What can you say about that?
You just change the Hamiltonian locally along this line, and basically like you apply translation only one side of this defect line, and that gives you the kind of usually like a twist lines, right? And the anions passes this line changes anion charge. We have a microscopic model for that kind of defect line, and if this defect line arranged periodically, separated only by one unit, that gives you this model. So you can start from the original toric code and arrive at this model by that way. Symmetric arrangement of defect lines. The kind of continuous description will be given from that kind of direction. Yeah.
Can I ask a question on the
about
eating model? So if you in that case, if you compute the local correlations function separated with the space, and if you make them sufficiently separated, how does it behave?
Oh yeah, so
does it
in the symmetry-broken case?
show some weird behavior as in the case of
yeah, I think so. Yeah. So, but so you are talking about like long range correlation. Yeah. I think it shows such kind of way. Yeah.
Without the ground state degeneracy.
Right. Wait.
It's gap, right? It's a gap, right?
But that is true for any usual ID model, right? Because in the usual ID model,
in that case, but in the infinite volume ground state is degenerate, so that's
degenerate means like just two-level degeneracy, right? It's not really like only Laplace excitation. It's really just
but so I mean, so if I take, for example, cat state, so ODL-RO detects so violation of the cluster decomposition property, and we can detect the degeneracy.
Yeah, okay. So if you are talking about like the violation of clustering, for the unique ground state, maybe it's not the case. I'm just saying like you still see some kind of long range correlation.
Long range correlation.
Yeah, so that means like I have like a non-zero expectation value of the order parameter itself. So so for this model, like, you don't have to look at the long range order, like So yeah. Yeah, okay. So this model is really kind of crazy, like as I said, like you have a here I'm using a reason loop operator as a symmetry operator, right? That's a reason loop operator for the INT model. Yeah, but as I said, like depending on the system size, it is really like an exact symmetry or non-exact symmetry, right? It has some mismatch at the boundary. In that case, it is not really an exact symmetry with the model. So
I see.
and so usually like if you switch off your symmetry breaking field, the order parameter goes to 0. So this is like log plot. But for that choice of system size, if you turn off your symmetry breaking field, the order parameter doesn't goes to 0, but instead it becomes some other value. But if you increase your symmetry breaking field, then you can reach to other value of order parameter. And then the minimum symmetry breaking field required for this kind of jump decreases as the system size increases. So that kind of gives you the non-commuting nature of symmetry breaking field. And this non-zero value of order parameter, maybe this explains the long range correlation function.
Yeah, that's interesting.
Yeah.